Hello, Science 30. This lesson is on titrations, acid-base titrations. And what a titration is it is a lab technique to quantitatively determine the concentration of a solution. So when we say quantitatively, we're not just saying that a solution is more or less concentrated in general terms. What we actually want is a number for the concentration. And when we're talking about concentration, the units that we are talking about are going to be in, and we'll see this later with some calculations, moles per liter. Moles per liter are the units that we're talking about. So the unknown solution is, for Science 30 anyway, what it is typically going to be is a sample from the environment that we're going to be determining how acidic that solution is. So this solution that we're talking about here, I'm just going to say that it is solution A, and that's appropriate in this case because it will be an acid solution. So how we do this, a solution of accurately known concentration. So this one here, solution A, we don't know the concentration of it, but we do need to have another solution that we do know exactly what the concentration is. And this is called our standardized solution that we're going to use. So that one again has a specific and known concentration. So as we'll see, it is going to gradually be added, delivered from a burette into our other solution, which again is our solution A of unknown concentration. And we're going to allow a reaction to take place until the reaction is complete. And because it is an acid and base reaction, what's going to happen is we're going to have the neutralization taking place. So we're going to have our acid. We're going to be adding some base. So the acid itself would have a pH of less than 7. The base would have a pH on its own of a greater than 7. But on the other side here, we're going to get our products, and that is going to have a pH which is now going to be neutral. It's going to be equal to 7. So our accurately known solution then that we're talking about, the standardized solution, again, that is going to be a base, so we'll just call that our solution B. So acid solution, base solution is the reaction that's going to be taking place. So the picture down below is what it looks like. So in an acid and base titration, our standardized solution, so this is our base here, the sodium hydroxide, is going to be put into a burette. And this is a burette that we're taking a look at here. So we have a retort stand, we have the clamp that is holding the burette, and the burette allows us to deliver a very, very specific volume of solution. And in this case, it's going to be the sodium hydroxide that's being delivered. The other solution that we have, our acid solution, it goes into this Erlenmeyer flask that we have here. So that's what they're showing is our acid solution. And we're going to be using a pipette, which again can deliver a very specific and accurate volume. And here they're saying that that is 20 milliliters. So for our acid solution, the volume then, we're going to know what that is. It's the concentration that we're trying to figure out. For our standardized sodium hydroxide solution, the concentration, we're going to know what that is. And after we deliver a certain amount from the burette, we're going to know what the volume of that is as well. So we're going to have two volumes that we know. We're going to have one concentration that we know, and that's going to allow us to calculate the second concentration that we don't know, the concentration of the acid. So the way that this burette works is up at the very top here. This is the initial volume reading. So you're going to fill up the burette till it's just down below this 0 level. So this right here is 0 milliliters. It is measured in milliliters, and most burettes, they range from between a 25 and a 50 milliliter burette. Those are the common ones. Down at the bottom here, if this is a 25 milliliter burette, this would be the 25 milliliter volume down here. So if we do have our initial volume right on 0 milliliters, and then we deliver the solution out of the burette and into our acid solution, then we're going to have a final volume at the bottom here, and maybe this is going to be 22.7 milliliters. So how do we determine the amount of volume that has been delivered? Well, we just subtract the final volume from the initial volume, and because the initial volume was 0, it would end up being 22.7 milliliters. In fact, with the burettes, we can measure to 2 decimal places. So we can actually record this to 22.75, for example. So very, very specific volumes that can be delivered. So how do you know when that reaction is complete? Well, when we have neutralized the acid with the base solution, we refer to that as the equivalence point or the end point, but it really is when the neutralization has taken place. So how do you actually tell that this neutralization has occurred? Well, what you're also going to add to the Erlenmeyer flask along with the acid is going to be an indicator. And this is going to be an acid and base indicator. Indicators are different colors depending upon what the pH of a solution is. So the indicator that we typically use for an acid and base titration like this is called phenolphthalein. And in acidic conditions, it is going to be clear. And in basic conditions, it's going to be pink in color. So initially it's clear, and then you're going to keep adding the sodium hydroxide out of the burette. And when you do have the equivalence point that has been reached, all of a sudden it's going to switch from a clear color to a pink color. And that is how you know when to stop delivering the amount of sodium hydroxide out of the burette and what the volume of sodium hydroxide is that you had to add in order to reach this equivalence point. So a couple of pictures here. The graph, first of all, so what it is showing is our acid solution and the pH of the acid solution. So initially, our sample from the environment, it's showing here that it is down below 7, so it is an acidic pH that we do have here. If we take a look at the pictures down below, this is the Erlenmeyer flask. So right at the start here, we would only have the acid solution, and then up above, we can just see the bottom portion of the burette. This portion right at the bottom, it's called the stopcock, and that's what allows you to allow the solution, the sodium hydroxide solution, to go out of the burette and drip down into the Erlenmeyer flask. So initially, you typically open it up fairly quickly, allow the solution to drain out, and what we see is that it doesn't really change the pH all that terribly quickly, but then all of a sudden, this steep part of the curve here, all you might need to go from this point where it's acidic to where it's neutral, it might be the difference between 1 drop of the base or maybe even just half a drop of the base. So if we do take a look at this Erlenmeyer flask at the end here, this one here in fact is too dark, and you have gone too far in terms of going past the equivalence point and adding too much base. So for your first trial, and you usually do a titration multiple different times on that solution to again make it more accurate, usually your first one is kind of a rough one and it ends up being too dark, so you actually don't count that one. But then you do it a couple of more times once you get a rough idea of how much solution you're going to be delivering from the burette. So ideally, you want what we call a pale but persistent pink. It has to be pink and it has to stay pink. So when you swirl around the Erlenmeyer flask, the pink cannot disappear and go back to clear. If it does, that means you need to start adding some more base, probably very, very slowly, drop by drop, or maybe even less. Get a drop hanging at the end of the burette right here. Touch it to the inside of the Erlenmeyer, make it part of the solution, and that might be enough, half a drop, to turn it from the clear to the pink solution. So that's what you're looking for, a very, very specific volume of the sodium hydroxide that is added in order to get this color change, in order to reach the end point, and that would be what I circled here with the small circle right here. So this is our end point in terms of this acid and base titration. So what is actually going on inside of the Erlenmeyer flask with this neutralization reaction? If we jump ahead here a little bit, so we have sodium hydroxide, which is in the base. We have hydrochloric acid, which is in the Erlenmeyer flask, or sorry, the base that's in the burette. the hydrochloric acid that is in the Erlenmeyer flask. So when we add the base into the acid solution, remember that acids donate protons. So these protons here, the hydrogen and the positive charge, are going to be donated over to the sodium hydroxide, which is actually split up. It's dissolved in the solution, it's formed the ions, and now the proton is going to be donated over to the hydroxide. And what that actually ends up forming, well, is just water. So what are we left with? We're left with the chloride. We're left with the sodium. On the right-hand side, I have it written here as sodium chloride. But in reality, what we're going to have is just salt water. We're going to have the sodium ions, and we're going to have the chloride ions that are dissolved in the water. And there's nothing here that's going to make it an acidic solution or make it a basic solution. So now again, on the right-hand side, the pH is going to be equal to 7. So once you've done the titration and you have your numbers of the sodium hydroxide that's been delivered out of the burette, now what do we actually know? Well, we know the concentration, once again, of our standardized solution, which is the sodium hydroxide, and we'll just call that here C1. We know the amount of sodium hydroxide now that was also delivered from the burette, the volume, so we know that. So the number 1 here and the number 1 here, we're talking about the sodium hydroxide. Okay, those numbers go together and they are for the sodium hydroxide solution. Inside of the Erlenmeyer flask, this is where we're trying to figure out the concentration of the acid. We don't know that, but what we do know is the volume of the acid. So now I have here V2. So in this case, the 2 is specific for the acid. So the number 1 is specific for the base, the sodium hydroxide. The number 2 is specific for the acid. So that means what we're trying to find out is the concentration, C2, and that one will be the concentration of the acid. So as long as we have 3 of the 4 variables, 2 volumes and 1 concentration, that will allow us to calculate what the concentration is of the acid, which is what we are trying to do. So the coefficients in this balanced reaction are going to show us what the molar ratio is going to be. So if we take a look at this reaction again here, this reaction is already balanced. We have 1 mole of sodium hydroxide reacting with 1 mole. It's a 1-to-1 molar ratio that we do have. Okay, it's just a 1 over on these ones as well. A 1-to-1 molar ratio. If you go to your data booklet, this is the stoichiometry and solutions formulas in your data booklet that you do need to be aware of. So this one here, first of all, concentration again, capital C. If we take a look over at the right-hand side, as I already mentioned, the units are moles per liter. So lowercase n, that is for our moles, and capital V, that is for our volume. And here they do have it again in liters. So it is moles per liter for the concentration. The other equation, this is the one that we're actually going to be using here. So here they have it as CI, which is for initial, VI, initial. So for our solutions that we're talking about, that will be either the acid or the base solution. The final, the F, that will be the other solution that we're talking about. So what I like to do is I like to change it up a little bit. So rather than just writing CI, CF, VI, VF, or even using the 1 or 2s, I actually like to indicate what the solution is, or at least put B for the base and A for the acid, just so I don't kind of mix up what goes with what. So the concentration for the sodium hydroxide has to go with the volume for the sodium hydroxide. Overall though, this of course is the equation that we're going to be using, and we use it in this form here because we know the number of moles are going to be the same, and moles are equal to concentration times volume. So the concentration times the volume of the sodium hydroxide is going to be equal to the concentration times the volume of the hydrochloric acid, because it's a 1-to-1 molar ratio. What we want to do, though, is take this equation here and we want to rearrange it because we know this volume, we know this concentration, we know this volume. What we don't know is this. Again, I'm going to rewrite this just a different way. So what we're trying to find out is the concentration of the acid. That's what we don't know. We now know the volume of the acid, and we know the concentration of the base, and we know the volume of the base as well. So we want to rearrange this equation to get this on its own, which means the volume of the acid, it needs to go on the other side of the equal sign. So simple way to do that. All of these, it's just as if they're over 1. Everything we have so far is in the numerator. If I want to get rid of this volume and move it to the other side, I need to cancel it out. And that means I need to put it in the denominator, and then they cancel out. But the rule is whatever you do to one side, you need to do to the other side. So if I divided the left-hand side by VA, I need to divide the other side by VA. So now I got rid of everything on the left-hand side except what I'm looking for, the concentration of the acid. What is it equal to? The concentration of the base times the volume of the base divided by the volume of the acid. Again, all these equations and what the different letters, the symbols represent, all of that is given to you in the data booklet. So none of that you need to remember. And this again is just a rearranged equation. And yeah, typically this is always the way that you would rearrange it, especially for Science 30, because this is typically always what you are solving for, which is the concentration of an acid. So let's take a look at an actual calculation here. So calculate the concentration of 30 milliliters of hydrobromic acid if 17.5 milliliters of 0.2 moles per liter sodium hydroxide is added to reach the end point. So the reaction that we have going on here, if we just write this, what do we have? We have hydrobromic acid, which is HBr. We have sodium hydroxide, NaOH. This is also a 1-to-1 molar ratio. And what we're going to get on the other side is going to be our water plus our sodium ions plus our, this time, bromide ions, essentially salt water again that we're talking about here. That is the reaction. Grasp, what is your given information? We'll take a look at the numbers. So we have a number here. Milliliters is for volume, so we're given a volume. What is this the volume for? That's the volume for the acid. So I'm going to write this as VA. We know the volume of the acid, and again, this would be what is put into the Erlenmeyer flask. What else do we know? We have another volume. Milliliters is another volume. This one here is now for the sodium hydroxide, which is the base. So we have a volume of the base of 17.5 milliliters. And we have one more number. Units are moles per liter, so that's the concentration. And that's the concentration of the base. And it's equal to our 0.2 moles per liter. So you always need to tell me the given information. Always include the units as well. And what are we looking for? What is the required information? Well, we're trying to find the second concentration, and that concentration is for the acid. So that is our unknown. That's what we're trying to figure out. So your A is the analysis. That's your equation. So it is, and I'm just going to show the rearranged form here. So the concentration of the acid is what we're trying to find out. That's equal to the concentration of the base times the volume of the base divided by the volume of the acid. All of these we know. Solving is plugging in the numbers with the units and coming up with the answer. So concentration of our base from over here, it is the 0.2 moles per liter. We're going to multiply that by the volume of the base. Don't mix these up. You need to make sure you're putting the volume of the base and multiplying it by the concentration of the base. So if you put the 30 milliliters in here, then you would get an incorrect answer for that. So make sure you keep your volume and concentration for the base together, dividing it by the volume of the acid, which is the 30 milliliters that we now have. Normally, you would have to have all of the same units. So normally you would convert these into liters as well. Those are the standard units. But fortunately, you actually don't have to for these reactions, or rather for these calculations, because milliliters, they just cancel out in. So we don't need to worry about that. What are we left with? We're left with moles per liter. Those are the units for concentration. So this is one of the reasons for always showing your units, so you can confirm that what you actually do get for your units is what you're looking for, which is a concentration, and in this case, the concentration of the acid. So when you plug these numbers into your calculator, you get 0.116666, and then there are probably a bunch of numbers after that as well. So pay careful attention to how they want you to record your answer, especially if it is numerical response. So with numerical response, there are 4 boxes. And typically what they say is something like record your 3-digit answer. So that's what I'll write down here. So in brackets down below, they will say record your 3-digit answer in the numerical response section. Record your 3-digit answer, or record your answer to 3 digits. A decimal is not a digit, but all numbers are a digit, including this 0 in front. So I need to put that 0 in. I put the decimal in here. I have 1 digit. I need 2 more digits. Okay, this is 1. I need 2 more digits to give a 3-digit answer. So if I put in 1, 1, that's actually incorrect. What you need to do is you need to round. So you need to take a look at the next digit. If it is equal to or greater than 5, you actually bump this up. So for questions like this, they're asking you a few different things. Can you do the calculation? Are you following instructions in terms of how to record your answer? And do you know how to round properly? So the correct answer here, the only correct answer, would be 0.12. You may also be asked to calculate the pH. So pH is equal to the negative log of the hydronium ion concentration. So I didn't put the hydronium ions in here, but if we do have our acid solution, it reacts with water and it forms hydronium ions. We do have an acid and we're trying to figure out the acid concentration, but the hydronium ion concentration is the same as a strong acid concentration. So we're just going to say that those are equal. So what I'm going to put in here is the concentration of what I just calculated, the acid. So when you do this calculation, though, make sure you don't use your rounded number. Make sure you use all of those numbers that were originally in the calculator. So the negative log of 0.116666 and however many more there are, that's the number that you're putting in order to get the pH for this solution.